This video is on delta H's, or changes in enthalpy. The units often given are either kilojoules or kilojoules per mole. There are several different types. I'm going to focus on one of them to a greater extent in this video. The first delta H you might have heard of is a delta H of solution, which is illustrated by this equation right here. And in this equation you can see when 1 mole of ammonium nitrate dissolves, forming 1 mole of ammonium ions, 1 mole of nitrate ions, okay, 25.4 kilojoules is going to be absorbed. And the only thing I want you to take home with this one is the idea that since energy is being absorbed, the solution will feel, okay, cold, because the surroundings are literally the solution that the substance is dissolving in. So if you have a solute that's dissolving and it's exothermic, the solution is going to feel warm, the temperature is going to rise. If it's endothermic, the temperature is going to drop. Okay, the second type of delta H is delta H of combustion. Not much to say about these except they are highly exothermic, which means they're going to have a delta H that is a negative value, and there'll often be a very large negative value. The one I want to focus on today is the delta H of formation. The delta H of formation describes the formation of 1 mole of a compound from elements. Now this is really important, from elements. So if you're making something from, like, you can't have a situation in which you have 2 compounds on the left making a bigger compound. This is literally a compound on the right and elements on the left. And those elements have to be in what's called their standard states. And that's what this big little 0 state refers to, what's called standard state. So what this standard state really needs to be defined here. Okay, standard state means if it is a gas, the pressure is 1 atm. If it's a solution, it's got to be 1 molar. And also, it's the formula something would be in, and the state it would be in at about 25 degrees Celsius. So for oxygen, the O2 would be a gas, whereas for mercury, it would be a liquid. And make sure we're clear, this is not the standard state of oxygen. All right, so when we talk about the standard state, is what form would the element normally be in, okay, at 25 degrees Celsius in the pressure of 1 atmosphere. So basically, if it was in the room in which we're working, what would it be? So a metal would be, except for mercury, would be a liquid. Fe would be this as a solid, and all your diatomics would be diatomic. So what I'm going to do right now is I'm going to write out 3 of the heat of formation equations. They have a very specific form. First thing you want to notice is the product will always be a 1 here, or it won't be written, but it means there's 1 mole of that thing made. And note the phases here. Aluminum oxide is an ionic compound, it's a solid at room temperature. Ammonia is a gas, and methanol, which is a type of alcohol, okay, is a liquid at room temperature. And so they'll have the correct phases written next to them. On the left-hand side, we're going to put in the elements. Now, to make 1 mole of aluminum, we're going to need aluminum and oxygen, the elements that compose it, right? So the equation for the heat of formation for 1 mole of aluminum oxide would be 2Al, and aluminum is a solid at room temperature, so we'd have the S. And for oxygen, we're going to have O2 over here, so we're going to have to do a little bit of weirdness, which you're going to see a fraction here, because 3 times 2 is 6, 6 divided by 2 is 3, and it gives us 3 oxygens, and this is O2 as a gas. Right, so we don't change these subscripts here to make it match what you have over here. We do something with the coefficients to make it match, right? And sometimes we have to use a fractional coefficient. You see that a lot in these heats of formations. All right. For the nitrogen here, we have N2 on this side, and we have H2. So in order to do that, we're going to have that's my G, by the way. That's not an S. Sorry. Okay, we're going to have 1/2 of the N2. Plus, we're going to have, again, 3/2 of a hydrogen to make our 1 mole of ammonia. And the same thing over here. And we have to be very careful. So this is going to be 1 carbon. Carbon is a solid, by the way, right? It's like charcoal, right? They have oxygen, but there's only 1 O over there. So we're going to have 1/2 of an O2 as a gas. And then we're going to have this 4 hydrogen there. So we're going to have to basically take 2 times H2 as a gas to cover us. Those are your heats of formation. One other thing you might want to notice here is the values here. Okay, In terms of stability, the more exothermic the process involved in making the compound, the more energy you would have to put into it to decompose it. So compounds which are have very large delta H of formations that are negative like this, in which the process is very exothermic, tend to be very stable, comparatively speaking. And you can think of that in terms of potential energy. Things of high energy are unstable, like balls tend to fall down, not up, right? Because things are more stable when they move close to each other if they're attracted by gravitational force. Compounds tend to be more stable if during the process, here's your potential energy diagram, right? You went like this and like this. This is low potential energy. Okay, this is a big negative delta H, and that means this is equal to a very stable compound. So of these three compounds, you pretty much assume aluminum oxide is the most stable because the process to make it is the most exothermic. So we can use the heats of formation to figure out the overall delta H for a reaction. If you view a reaction as basically a change in which some compounds are unformed and then some compounds are formed, you can see how we can do this. So you can view this as the CH4 basically is going to be unformed. So if we figure out what the delta H was to make CH4 and we sort of unmake it or negate it, so we turn it from a negative to a positive or vice versa, okay, we can use that, okay, to figure out what it took to get to this step right here. And then we can take these elements now that have been formed from the unforming of the methane, which is what CH4 is, and we can talk about, okay, here we're going to use the HFs. Okay, so here we're going to sort of negate the HFs, right? And here we're going to just take the HFs straight up because we're going to form these compounds. And this gives us a really, really simple equation. Basically, if the sum, okay, well, I'm sorry, that's a bad equation. The delta H overall of a reaction, okay, and I'm going to draw this probably, I'm not very good at writing out these formulas with these big things, is basically the sum of, okay, NF of delta H of formation of the products minus, okay, the sum of, with respect to the number of moles, right, of basically formation of delta H 0, 0 over here, 2, formation of the reactants. And what you can see is this big negative is the whole point. So you can think of, you're going to form some compounds in the products, add up the number of moles of each of those compounds. You make 2 moles of water, you're going to multiply the delta H by 2. You make 1 mole of CO2, you keep that as 1. But you're basically unforming this example, so CH4. So this negative here is really negating, okay, the HF of the reactant. And the reason why we're going to negate that is because the reactant is going to unform, as it were. So the final skill is being able to use these delta heats of formation to get the delta H of reaction, or to determine a heat of formation when you're given the delta H of reaction. And we'll do that. We'll do the first and sort of talk about how you do the second one. So let's say we want to figure out the overall delta H of reaction. Well, it's basically the products minus the reactants. The products are going to be forming. The reactants are going to be unforming. That's why you have this negative symbol to negate the actual values for the heat of formation. All right, because you're not forming them, you're unforming them, essentially. A couple things you want to notice here. First of all, you've got different values. Like HO is a liquid and N2 is a gas, M2 is a gas. Make sure they match what's in the equation, because if it doesn't match, you're going to have to use a different value. For instance, the heat of formation of H2O as a gas is going to be a smaller value, because you have to absorb energy to turn the liquid into the gas. So you get like negative 100 and something instead of negative 286. Second thing you want to notice is they don't give you any information about oxygen. And the reason why they don't give you information about oxygen is, by definition, the delta H of formation, okay, of an element in its standard state is always equal to the 0, which means you don't include them in your math, essentially, right? So, very simple work. You look at your products. Now, I'm going to not write out a lot of units here because I really want to just make it as simple as possible, okay? So you're making 4 NO2s and 6 waters. So you go 4 times 39, okay, plus 6 times negative 286, okay, and then here comes the negation, because we're now down to the reactants, and the oxygen's not including this, but the ammonia is. So you go, okay, how many ammonias? There's 4 of them. You go 4 times negative 46. when you do all the math here, and I'm not going to spend time, it's kind of easy math to do, right? Simple, unless you make silly mistakes. You end up getting a value of negative 1396 kilojoules per mole. Now you can use this value like, okay, what if I were to make, 8 moles of, of NO2? How much energy would be released? And if that was released into water, how much would the temperature of the water change? So you can take that value and determine what Q is under certain conditions and do the whole MC delta T thing and stuff like that. The other thing you want to recognize is they could have you solve for something. So let's say they didn't give you this number here, right? So they didn't give you this number, let's say. But they did give you this number. Okay, well, you can see how this can be a really simple algebra thing. So you go, 4 times 39 plus 6 times negative 286 minus 4 times, I don't even need parentheses, 4 times x, basically, right? And you solve for x now, and you get negative 1396. The one thing I will say for a lot of students is there tends to be difficulty keeping track of signs. Okay, if you do this properly, you should get a negative value. You should get negative 46 here. But you have to be super careful about keeping track of signs when you're doing the algebra, because if it's a multiple choice, they're going to give you positive and negative of the same number maybe. So you have to just make sure you're clear on what that value is going to be. All right, I hope that helps. Have a nice day.